Good morning, everybody. You're very welcome to this morning's webinar on seamless transition from number to algebra. We're delighted to have Sheelagh Clowry with us to facilitate. Sheelagh is a maths trainer, and I'm going to let Sheelagh introduce herself in a second. Just to say, it's great Maths Week. We've webinars on all week, so if there's anything else you want to have a look at, you can look at our website under upcoming events and see what webinars are on tomorrow, Thursday and Friday, and see if you want to register. You have to register for each one individually. Just on the questions, for anyone who's joined in the last couple of minutes, what we're hoping is that on your control panel, if you go down the side, on the right hand side, you've got an option called questions/chat. You click on that. As Sheelagh is presenting, if you have any ideas, any tips, any resources, or any questions for Sheelagh, if you type them in there, please. So Sheelagh will present for 30 or 40 minutes, and at the end around 20 to a quarter to 12, or whatever time she finishes. We're very flexible on time. I'll read out the comments, the ideas, the tips, the resources, and the questions that you have for Sheelagh. So over to you, Sheelagh, all the best.
Okay, good morning everybody, and you're very welcome. So Sheelagh Clowry is my name, and I'm broadcasting here from Moon in County Kildare. Now, I have taught mathematics to all levels in secondary school for many years, and I've also worked as a Regional Development Officer with the Project Maths Initiative, which is now embedded in secondary school curricula. And I've worked also with PDST and still work on a part-time basis with them. That's the Professional Development Service for Teachers, and part-time with pre-service teachers in DCU. So that's it. And that's my introduction. But my main interest in teaching mathematics is in sense making of mathematics for students, because this enables them to use mathematics with confidence. When they see that maths make sense, well then they say, okay, anybody can do this, which is the case, of course. And I must say, I just want to say to all of you that I really admire the work that you do in instilling confidence in adult learners, because it just boosts their lives in so many ways, and I take my hat off to you. So it's a privilege to be talking to you here this morning. So what we said, we want students to see maths as sense making, so we definitely want them to see algebra as sense making. And algebra is inextricably linked to number. So I'm suggesting to you, why not teach algebraic thinking alongside number as they're going along, rather than say have students come to a chapter which is called algebra, and they're suddenly bombarded with all these expressions and symbols that somebody else has generated, but they've never made an algebraic expression themselves. So this seems like something completely obscure to them. So what we're going to do is we're going to generate our own expressions, and then hopefully make sense out of all these expressions with symbols, and we're going to do it in number. So we'll look at some simple examples of how we can teach students what we're going to call algebraic habits of thinking. And as I always say to teachers, I don't tell my students that I'm doing algebra at this point. I say to them that I'm generalizing, and I use that phrase generalizing quite a lot. But what I'm doing here is trying to acclimatize students to the use of symbols. So before they come to the chapter called algebra, they will be well used to using them and understand them. Okay, so what are these algebraic habits of thinking that we're going to be using? We're going to form generalizations from experiences with numbers and computing with numbers. So it's going to be constantly rocking back and forth between number and symbols. We won't be dealing with symbols full-time or with number full-time. We'll be doing and undoing. So if a student does some computation, we'll ask them, how would you undo that? And that's how we'll teach them to solve equations. We will build rules to represent relationships, and you will see that happening as we go along. And the very last thing that we do in each section is to bring in symbols, because that's historically how algebra happened. The symbols didn't come in until about the Renaissance. Okay, so what does research tell us about the best ways to teach algebra? Well, they say best practice links algebra skills to number skills. So that's why we're doing it this way. Begin algebra with relationships rather than procedures. So rather than teaching how to solve, how to factorize, we will gradually find ourselves doing these procedures through relationships. Teach the skills in different ways to reach a variety of learners. Now, you're all very experienced as teachers, and you know that everyone in front of you maybe learns in a slightly different way, which is why we need to vary the way we present information. Avoid informal shortcuts. So the classic one here, I suppose, is when solving equations that students sometimes have been told, bring it over and change the sign. And that is a rule really without a reason, and it also leads to errors and misconceptions. But we'll deal with that later. Teach algebra as a useful and convenient problem-solving tool. So algebra does relate to real life. It allows us to do things very easily in real life and to solve problems very easily. We don't want students to think of algebra as being something obscure and pointless. And then the importance of mathematical literacy. So it doesn't matter what field you're involved in. I mean, if you're playing rugby, there's a certain vocabulary going with it, or you're playing golf, there's a certain vocabulary going with it. You don't learn that vocabulary by definitions. You learn it by gradually playing the game using these words in a natural way. We'll do the same when we're teaching algebra. So we're going to treat number as the groundwork for algebra. Now, the literacy, all these words I'm going to put up on the screen now. Hopefully, when we finish, that we will have seen how students can use them with understanding. Variable, constant, expression, evaluate, term, like terms, simplify, equivalent versus equal, equation, solve an equation, inverse operation, factor. Okay, we're not going to put up definitions of these, but we're gradually going to acclimatize students to them. So let's get started. So this is the practical bit. We have the introduction over. So what you see in front of you here is a pattern of numbers. And when you see a pattern, that's wonderful, because a pattern allows you to predict what the next number is in the pattern. So we say to students, what's the next number after 6? Okay, it's 7, and they'll all be, what's the next number after 7? That's 8. Now we could say to them, can you express 7 in terms of 6? So we're changing the language a little bit here. How do we get to 7 from 6? So hopefully they'll say it's 1 more than 6. How do we get to 8 from 6? Hopefully they'll say it's 6 plus 2. Right? So now 6 plus 1 is an equivalent way of writing 7. 6 plus 2 is an equivalent way of writing 8. What about the number before 6, which is 5? How do we express that in terms of 6? Well, hopefully they'll say it's 6 take away 1, and 4 is 6 take away 2. So now, if we were at any position in this list, wherever we're at a particular number, the number after that is 1 more than the number. The number before it is 1 less than the number. If I write that all down in English, it's a long sentence and it's a little bit confusing. But mathematics is all about making life easy. That's what students need to remember. So it was decided that we would represent a number in this list using a letter. So I've chosen the letter R to represent any number in this pattern. Could I have chosen A or B or C or D? Yes, of course. I can choose any letter I like. When we choose a letter in this way to represent a number, we call it a variable. So there's R, it's representing a number, it's a variable. Now tell me what the number after R is in this list. So hopefully students will say, well, the number after 6 was 6 plus 1. So the number after R, since R is a number, must be R plus 1. And the number before R must be R minus 1. Now, you might say you haven't done a whole lot of algebra here, but however, you have introduced the basic idea of what algebra is about, which is about generalizing patterns that we see. So we have generalized, we have introduced the variable, we have seen that the variable, we can use any letter we like for the variable, and we've also connected the use of the variable to a very simple concept, a very simple pattern, where we're counting up numbers. Now, I wouldn't put up this definition of what a variable is next, but I'm just putting it here for you to just consolidate what we have done. When a letter or symbol is used to represent a number, with the understanding that a particular value hasn't been assigned to that number, we didn't say what value R had, and there may be a range of possible values that could be assigned to that number. Now that's a really powerful idea, that that letter could take on a range of possible values. It might only have one value, and then we call the letter a variable. So that's what we mean when we say when we're talking about a variable. Okay, we have another pattern of numbers here. This time, same pattern as before, but I've put some of the numbers in red and some of them in black. So you ask the students, what are the numbers in red called? What type of numbers are they? Now, hopefully the students will say they're even numbers. What type of numbers are the numbers in black? And we hope the students will say, oh, they're odd numbers. Okay, so pick any number you like in that list. Doesn't matter which number you pick, and multiply it by 2. So if I pick a red number and multiply it by 2, that's an even number. I get 4. That's an even number. Multiply 4 by 2, I get 8. That's an even number. Any even number I multiply by 2, I get another even number. Now look at the odd numbers and multiply them by 2. Right, 1 multiplied by 2, I get an even number. 3, I multiplied by 2, I get an even number. 5, I multiplied by 2, I get an even number. So what I'm saying is that any whole number multiplied by 2 gives me an even number. So I'll write it down in words. An even number is 2 times any whole number. It's a long sentence. Mathematics is a much simpler way, has much simpler ways of writing down sentences like this. So you know from the previous slide that we used a letter to represent any whole number. So this time I'll choose the letter P multiplied by 2, 2 by P, and that's an even number. Much shorter than writing down a big long sentence. Right, what if I had chosen X, where X is any whole number? Because I told you I could choose any number I like. Now there's a bit of confusion between the multiplication symbol and the letter X. So mathematics is all about making life simple, so it was decided that instead of the multiplication symbol, that the letter X would be put in brackets. So now I understand, and everybody understands, that if I see 2 bracket X, that means the 2 is multiplied by X. And mathematics can simplify this further. It was decided that instead of using brackets, that we would just write the number and the letter beside it. And we all understand that means 2 is multiplied by X. 2X means 2 multiplied by X. Now, it doesn't mean that when you write down 2, 5, the 2 is multiplied by 5. So you might have to bring that up in case students have an issue with place value, which they would have done before this. 5 means 5, and the 2 here means 2 tens. But we're talking here about a number multiplied by a variable. Okay, what have we done? We have generalized even numbers by using a variable. So if you see 2p written down, where p is a whole number, that's a way of expressing every possible even number in the whole universe. Okay, so it's very powerful. It represents an infinite set of numbers, and it can be written so simply. So we call 2p an expression, and it generalizes the pattern of even numbers. A letter symbol, we said before, can be used to represent a range of numbers, and not just one. Here it can be used to represent all the whole numbers. P can represent all the whole numbers. It's a very powerful idea. Which part of the expression is constant? Well, the number multiplied by p, 2, that's a constant. It doesn't take different values. 2 is 2. Now you could say to the students, evaluate the expression 2p when p is equal to 5. Now think of all the language we've been using so far. We have variable, we have an expression which generalizes a whole set of numbers. And now we're asking students to evaluate the expression when p is equal to 5. So if I change p, if I substitute 5 for p, 2 5s, that makes 10. What if I substitute 6 for p? 2 6s are 12. We're now doing substitution, which is often the start of algebra in textbooks. And that's no criticism of textbooks, by the way, because they have a different function. A teacher is much more powerful than a textbook. But the teacher is there to interpret a textbook. So when you substitute in here into an expression you have created yourself, then you understand what substitution is all about. Right, let's look at this list of numbers as well. So we have odd, even, odd, even, odd, even. So if b is a positive whole number, 2b is an even number. What about 2b plus 1? Well, let's go up here. 2b is an even number. If I add 4 is an even number. If I add 1 onto it, I get 5. 6 is an even number. If I add 1 onto it, I get 7. So every time I add 1 to an even number, I get an odd number. Now I have generalized odd numbers. So when I see 2b plus 1 written down, that's a really nice way of writing odd numbers. So if I have 2b plus 1, there's 2b. 2b plus 1 is the odd number after it. 2b minus 1 is the odd number before it. Okay, there's an even number. Add 1 onto it, I get an odd number. Subtract 1 onto it. From it, I get an even number. So we've generated lots of expressions here so far, and we're getting gradually used to the variable. Now, here's a cartoon you've probably seen before, and it's a situation where students get quite confused about the variable. So the teacher has introduced the variable in this way. X plus 2 equals 5. Box plus 2 equals 5. So the only value x can take on is 3. Now, if students are introduced to a variable in this way, they get the idea that a letter can only take on a particular value. So that's why the young fella is confused. He says yesterday he said x equals 2, because the person might have put on the board yesterday x plus 2 equals 4. Now in that case, x would have to be 2. So I would prefer students weren't introduced to a variable in equations first, because then they get the idea that the letter can only take on a particular value. So I would prefer that they're introduced to a variable through expressions. There's an expression like x plus 2. There's no equal to sign, there's no equation. Get them to generate numbers using the expression. If x was 1, well, 1 plus 2 is 3. If x was 3, 3 plus 2 is 5. And then you can say, what if the answer I got was 5 when I substitute a value for x? Like as in the cartoon here. Can you work backwards? What must I have substituted for x? Well, x would be 3. So the point there is I would say start with expressions first rather than equations when introducing the variable. Now you can disagree with me, of course, and some of you may have comments on this. Okay. What about this question here? Is x plus 2 the same as 2x? Now, how is a student supposed to know? Right, let's substitute a value in here for x. 3 plus 2. Is that the same as 2 times 3? No, it isn't. Could the left-hand side ever be equal to the right-hand side? So someone might say, well, what if x was equal to 2? 2 plus 2 is 4. That's the same as 2 2's. So that, I think, is why students get confused between x plus 2 and 2x, because sometimes when, for instance, in the instance when x is 2, x plus 2 is equal to 2x, but for all other situations it's not. But you have to empower students to check this out themselves first by using numbers, substitute in numbers, and see is it true. Now we'll look at more expressions. Okay, 3r. Well, we had 2r before, and that was multiples of 2, even numbers. So 3r must be multiples of 3. So it could be 3 1s, 3 2s, 3 3s, 3 4s, 3 5s. Oh, it's like the 3 times tables. It's a short way of writing down the 3 times tables. 5ts. Oh, now we've upped it a little bit. We have no sign between the 5 and the t and the s. That means they must all be multiplied by each other. And this time we've used 2 variables. So we could substitute in a value for t and a value for s. Now look at 8. 8, I don't see a variable multiplied by that. 8 is a constant. 8 is 8. So there is an expression with a single term, an expression with a single term, an expression with a single term, and then we could combine all those together by addition or subtraction. Now we have a new expression, but this one is made up of 3 terms. So what is a term? A term could be a constant on its own, or it could be a constant multiplied by a variable, or it could be a constant multiplied by one or more variables. Now you might not want to introduce this word here, and I didn't introduce it in the initial set of words, but if you want to, you could introduce it. 3 is called the coefficient of that first term, and 5 is called the coefficient of the second term. Now, when a teacher knows the students in front of them, you know the students in front of you, you know how far to go. And in any one class, this might be far enough to go without continuing on with what we're doing. So give students time to get used to what a variable is. It's a letter which represents a number. Now, the only time in mathematics that a letter doesn't represent a number is when you have a space between the number and the letter. For instance, 2 space m. That would represent 2 meters. Okay, there's space between the letter and the number. And the m won't be in italics when it's written down. So it's only if the letter represents a unit. That's the only other time. Every other time, a letter represents a number. So we have an expression which can be a single term or a whole lot of terms added together. Now, I have actually spent quite a lot of time talking about expressions and terms and variables. And what I said to you before is sometimes students get that expression like 3r plus 5s, something like that, as their first introduction to algebra, and they've never actually talked about what does the expression mean. So now let's go back and recap a little bit. R and S are any 2 whole numbers. What does R plus S mean? Now this is a discussion you have with students. So it is the sum of any 2 whole numbers. And I can substitute different values for R and S. Is it the same as RS? Well, no, we said that means R multiplied by S. Is R plus S the same as S plus R? Verify. How am I supposed to know? substitute in values. So you don't have to ask the teacher why. So if R was 3 and S was 2, 3 plus 2 is the same as 2 plus 3. Notice we're always relating these symbols back to numbers. What does RS mean? It means one whole number multiplied by another whole number. 4 by 2. Is it the same as 2 as S by R? How do you check? Substitute in values. Is R plus 2 the same as 2R? Now I have that one in red there because we talked about that a few minutes ago. Is X plus 2 the same as 2X? Now I've written beside this here context. So for instance, if you said, I said I was 2 years older than my sister, is that the same as being twice as old as my sister, where my sister's age is R? So that's 2 years older than, and that's 2 times older than. What does 3R minus 5S mean? Asks you to explain expressions like that. It's 3 times a whole number minus 5 times a different whole number. So at this point, you get students to generate and explain their own expressions, which can include variables and constants. Now, look at that sentence there. There are a lot of words in that they wouldn't have known at the beginning of this. Now they can understand what I mean by those words, or that's the idea. Hopefully they can understand the language of mathematics. And then evaluate your expression for different values of the variable used. Again, if I introduced 3R minus 5S at the start of this and said, here's an expression, evaluate your expression for different values as variables, they wouldn't really know what I was talking about. Now we'll move on to the next section, which is a very important part of algebra, and we will be talking about solving equations. Now notice that first part was all about expressions. We didn't have equal to signs in it. As soon as you put in an equal to sign, you have an equation. So in the calculator, the equal to sign means evaluate. 5 plus 3 plus the equal to sign, it will evaluate that, give you a single number answer. Now that's another thing that students have an issue with. When you say 5 plus 3, they end up getting one number. When you say X plus 2, they kind of want to compress it into one number, which is why some of them say 2X, without thinking about their not being the same thing. So X plus 2, leave it as is, X plus 2. Okay, I can substitute in different values. Anyway, the equal to sign means has the same value as. So 3 plus 6 equals 9 really means it has the same value as 9. It doesn't mean do a calculation. 9 plus 2 equals 11. 9 plus 2 has the same value as 11. This is an error students make sometimes. Okay, I have €3. Someone gave me €6. I end up with €9, and then someone else gave me €2. How much do I have altogether? And they write down something like this, which of course doesn't make sense mathematically, because 3 plus 6 is not equal to 11. So they have to be very careful in the use of the equal to sign. What's on one side of it is exactly the same as what's on the other side of it. So ask students to give more than single word answers in number, because we don't want them to think that equations are something they meet in algebra. You meet equations in number, of course, as well. So when you say, what is 16 plus 8, for instance, you know, that they say 16 plus 8 equals 24, which means 16 plus 8 has the same value as 24. But a student who writes down 16 plus 8 is equal to 10 plus 14, they're totally correct. Left-hand side equals right-hand side. And you could get students to write down 16 plus 8 in 10 equivalent forms. You know, it's 48 divided by 2. 16 plus 8 is 24, but you could also say it's 30 minus 6. So getting students to play around with numbers like this is great for number sense. And if they're not sure if they've come up with an equivalent form, like here, they can use the calculator to check, are they correct? So remember, equations, or for your students to remember, I know you know, always have an equal to sign. So there are equations there. Now, games like Countdown are great. You've probably seen a TV version of this. So let's say these are our target numbers. And I want you to combine numbers using various operations and various numbers to make up these numbers here. You can make up the rules. Use each number only once for each calculation. Okay, so these are the numbers that you can use: 10, 50, 100, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I want to end up with the target number of 253, so I could have 100 multiplied by 2 plus 50 plus 1 plus 1 plus 1. You know, several ways of using all these numbers and all these operations. And this is a way of using your calculator in a creative way, as opposed to me giving students, you know, work out 47 multiplied by 2 plus 6, something like that. I'm just going to press my Windows button here to show you. I have an emulator. Hope you can see it on screen. This can be very handy when you're showing students how to use a calculator. And there's a very convenient button here on the screen, and it's called a fact button. Now, I know this is a particular type of calculator, and it's one I'm very fond of. It's the Casio calculator because it can do lots of convenient activities or computations. So I press Shift and Fact if I want to use this button. Okay, the first thing I'm going to do is put in 9, press equals, and that's gone into memory. Then I go Shift and Fact. And the calculator writes it for me as 3 with a little 2 above it. Now, if students haven't seen that little 2 above it, they'll say to you, well, what does the little 2 mean? And you say to them, well, what do you think it means? Okay, does it mean 3 multiplied by 2? No, that wouldn't be right, because that would give me 6. It must mean 3 multiplied by 3, because 3 by 3 is 9. So that's a short way of writing 3 multiplied by itself, 3 squared. And then if you put in 49 and you press equals, okay, then goes Shift and Fact. Okay, that gives me 7 squared. So that means 7 multiplied by 7. I wonder, what does x squared mean? Well, it must mean x multiplied by x. What does b squared mean? It must mean b multiplied by b. And is that the same as 2 times b? Or is that the same as b plus 2? So now we've looked at x plus 2, 2x, and x squared. And there are 3 expressions that students often mix up, but relate them back always to number. Now, you can use this button, of course, to get the factors of any number. 84 equals, and then I go Shift and Fact. There's my Fact button. Okay, it'll give me all the factors of 84. So you might or might not want to use that. Anyway, it's very useful. Next thing we're going on to is adding like terms. Sorry, just go back there for a second. How are we currently doing it, and does it cause any misconceptions? So I want you to just think for a few seconds there about how you currently deal with adding like terms. Okay, now I'm going to show you some student work here. The student was given this question. It was a sort of a diagnostic test on algebraic thinking. Algebra cost a cent each. So a cent, a is the number of cents that an apple. Did I say algebra? Apples cost a cent each. Bananas cost b cent each. If I buy 3 apples and 2 bananas, what does 3a plus 2b represent? Okay, so it's 3 times the cost of an apple plus 2 times the cost of a banana. So it's the total cost of 3 apples and 2 bananas. Now here's what the student wrote. They said it's 3 apples and 2 bananas. And having asked the student about why they wrote that down, what I discovered was that when they were introduced to the variable, they were told that 3a plus 2a is 5a because 3 apples and 2 apples make 5 apples. So 3a and 2a is 5a. So they were introduced to the variable a as an abbreviation of a word. And of course, 3 apples and 2 apples make 5 apples. That is a truth statement, but it causes confusion if students are introduced to the variable this way, because they think of the variable as an abbreviation of a word. So always introduce the variable, I would recommend it, as a number, the way we introduced it at the beginning. Now, so how would we add like terms then in algebra? So 2 plus 2 plus 2 plus 2 plus 2, rock back to number. Write that in terms of 2. A student will want to tell you it's 10. Would you say write it in terms of 2? So it's 5 2s, and we can draw a picture of it. You can see 5 groups of 2, or you can see 2 groups of 5. I hope you're not getting too tired at this stage. Just do a little bit more. Is everything okay out there? Yeah?
Yeah, 100%.
Okay. Yeah, it's, you know, when you're talking to a screen. I know.
Yeah, I know what you mean. It's a bit off-putting, but it's going great. Keep going, Sheelagh.
Okay, keep going. And is 5 groups of 2 the same as 2 groups of 5? Well, you could look across 2 groups of 5, or you could look down 5 groups of 2. Now, what if you had 927 plus 927 plus 927 plus 927? Well, represent that in terms of 927. It's 4 times 927. What about 7 eighths plus 7 eighths plus 7 eighths plus 7 eighths? Represented in terms of 7 eighths. It's 4 times 7 eighths. Okay, now what about b plus b plus b plus b, where b is any number? Well, we're just following a pattern. Simplify, it's 4b. Okay, so undo this then. What does 4b mean? It means b plus b plus b plus b plus b, 4 times. What about 3 5s and 3 5s? Now these are like terms. Okay, I have a number of 5s and the same number of 5s. So how many fibers do I have? Say if it was money, I have 6 fibers. Now what if I have 3x and 3x? Simplify, that gives me 6x, because x is just a number, like 5 is a number. Now here's student work. Okay, simplify 3x plus 3x. And the student wrote down it's 6x squared. So you really feel for that student, because they're not thinking of the variable in terms of a number. So you don't say to the student, you know, that's wrong. You say, okay, let's check this. What if you had 3 5s and 3 5s? Would that give me 6 times 5 squared, which is 6 25s? Well, no, and the student, they'll say, no, it doesn't. So when they're used to rocking back between number and algebra all the time, I think they're going to be able to self-correct here. That's the idea, that they will be able to do it. And this is another student trying to explain what they were doing here. They said x plus x equals x squared. So they were trying to remember rules or something, and they weren't thinking of the variable as being a number. And then they said x squared plus 3 is 6, and that's 6 plus x squared. And then they said 6 plus x squared is the same as 6x squared. So there are, you know, there's a whole forest of misconceptions tied up in that answer. So we always help students to correct their algebraic errors by using number. Now let's look at the following one, where we have different terms. 4 times 2 plus 7 plus 5 times 2 plus 3 7s plus 7. How many 2s have we got all together there? Well, we have 4 2s and 5 2s, so that's 9 2s. How many 7s? 1s. Now, by the way, there's no number written in front of 7, but that means 1 7. Same way when we have x, it's 1x. 1 7 and 3 7s and 1 7. Okay, 1 3. We have 5 7s. Let's use variables. Instead of 4 2s and 5 2s, we have 4a and 5a. Instead of 1 7 and 3 7 and 1 7, we have 1b and 3b and 1b. 4a and 5a, well, that must be 9a, because 4 2s and 5 2s is 9 2s. And then 4a, or sorry, 1b and 3b and 1b makes 5b. Simplify 4 times 2 squared and 5 times 2 squared in terms of 2 squared. How many 2 squareds have you? You have 9 2 squareds. What about 4x squared and 5x squared? You have 9x squared. And if you don't believe it, substitute in values. Now we come to what's very important in algebra. It's called the distributive law, but really, when you see the pattern in numbers, it's just a very big word for a very small idea, or very simple idea. 4 plus 4 plus 4 plus 7 plus 7 plus 7. And what a student will want to do is compress that into one single number using their calculator. But we want them to see what's going on behind the scenes when you add these numbers. So write this in terms of 3 and 7. So it's 3 lots of 4, sorry, in terms of 4 and 7, 3 lots of 4 and 3 lots of 7. Picture it, 3 lots of 4, 3 lots of 7. Could you look at it any other way? Simplify this in groups or in terms of 4 plus 7. So how many groups of 4 plus 7 do you have? There's one group, there's another group, there's another group. So we have 3 groups of 4 plus 7, or if we squash this picture together, put the 4 and the 7 bit together, there's a 4 plus 7, a 4 plus 7, and a 4 plus 7. So we have seen, you've actually seen what's called the distributive law, that 3 lots of 4 plus 7 here is the same as 3 lots of 4 and 3 lots of 7. Now, how that sometimes is introduced to students is if you have a number outside a bracket where you have terms added together, you multiply the number outside the bracket by everything inside the bracket. But that's giving it as a rule. Here we've seen, yes, it makes sense. Now let's use symbols. What about 3 times w plus 7? Well, w is just the same as a number. So it must be 3 times w plus 3 times 7, which is 3w plus 21. We talked in the beginning about undoing, doing and undoing. Could you go back from 3w plus 21 back to 3 times w plus 7? Just work in reverse, undo. Well, 3 times w, that's 3 times w. 21 is 3 times 7. So you have 3 times w plus 7. Now we've gone from multiplying an expression, and we've gone backwards, and we have the 2 factors of 3w plus 21. So we've learned about factorizing just by undoing multiplication. Now the student here, see what the student is multiplying 2 by 2x minus 5? Now they end up getting 4x minus 5. Maybe they've learned a rule, and what do you do? They didn't multiply 2 by minus 5, but what do you do if a student makes this mistake? Instead of saying to them, oh, you were supposed to multiply the number outside by everything inside, ask them to check their answer. So what they ended up with should have been the same as what they started out with. So if I substitute a number in for x in what I was given, and substitute a number in for x in what I ended up with, well, I end up with the same answer. So let's put in 1 for x. 2 ones are 2, take away 5 is -3. 2 times -3, that would give me -6. Put in 1 here for x, I get -1. So I didn't produce something which was equivalent to what I started out with, but I've checked myself and I can see that my work isn't correct. So try a numerical example. If we look at equations here for a minute, and I hope we're still all right on time. So 10 equals 10. What if I added 1 to the left-hand side and 1 to the, I'd have to add 1 to the right-hand side. Otherwise, I couldn't use the equal to sign. How do you go back, undo, from the second line up to the first? If I take 1 from the left, I'll have to take 1 from the right. Now this 10 take away 4 equals 10 take away 4. How will you end up going back to the first line? Add 4 to the left, but then I'd have to add 4 to the right. Inverse operations, addition and subtraction. If I want to work backwards from addition, I use subtraction. If I want to work backwards from subtraction, I use addition. Let's say 10 equals 10 again. What about if I multiply the left-hand side by 2? Well, to keep the equal to sign, I have to multiply the right-hand side by 2. If I divide the left-hand side by 5, I have to divide the right-hand side by 5. How do I work back up from the second line to the first? Use division by 2. How do I work back up from the third line to the first? Multiply by 5 on both sides. So where are we going to use this in solving equations? Let's say you're asked to solve for A. Now the student has to think about what happened here. I solve for A means I have to find out what A is. I started off with an unknown A. I subtracted 2 from it, and I ended up with 7. What was the last thing I did? I subtracted 2. So if I add 2 to the left-hand side, I will get A, but then I've got to add 2 to the right-hand side. I didn't say anything about bringing over or changing the sign. I'm undoing. So A is 9. Now go down to here, 5A equals 10. I start off with A multiplied by 5, I ended up with 10. Undo what you did, get back to find out what A is. Divide the left-hand side by 5. If I do that, I must divide the right-hand side by 5. Now if a student hears bring it over and change the sign, what they will do here, even if they divide by 5, they'll change that to a -5. But what I'm doing is using the inverse operation when I'm solving an equation. So I'm trying to get back to A. It was multiplied by 5. How do I get back? Use the inverse operation. Divide by 5 on both sides and get A equal to 2. So let's look at this equation here. Think of a number, say 5, multiplied by 3, you get 15. Add 4, you get 19. Now after this, I have only one other thing I'm going to show you, and then I will stop. Okay, you get 19. Write an equation to show how you got the output from the input. Everybody agree with that? 3 times 5 plus 4 is equal to 19. I've solved an equation. Let's use a variable instead of the input. 3 times C plus 4 equals 19. What should I use instead of 5? I used a variable. How would I find out what C is? Well, the last thing I did was add 4. I had C multiplied by 3 and added 4, I ended up with 19. Go in reverse. Subtract 4 from both sides. Now I'm down to 3C is 15. C was multiplied by 3. Do the reverse operation. Divide it by 3, divide both sides by 3. So you've now solved an equation using undoing. So you undid, to form this equation, you did certain operations, and then you undid them step by step to solve the equation. Hopefully we have hit all this language on the way. Let's look at the last example. A plumber charges €50 to make a house call and charges €30 per hour for labour. Now what's constant? What doesn't change, regardless of the time the plumber spends in the house? €50 for the house call. What is varying? Right, the time is varying, isn't it? The €30 per hour is also constant. And the charge at the end of it is varying. So we have 2 constants, the house call and the amount per hour. We have 2 variables. The time he's going to spend and then the money he's going to charge me, which depends on the time he's in the house. Represent this situation using a table. So let's say we have a table, no hours spent, 1 hour, 2 hours, 3 hours. If the plumber spends no hours, he just comes to the door and then he goes away. That's 50 euro, okay? Or if you leave in your laptop to be serviced, you have to pay 50 euro up front and then so much per hour. So if he stays 1 hour, add on 30. Stays 2 hours, add on another 30. Stays 3 hours, add on another 30. What if he stays 7 hours? Okay, that's not as easy to figure out now. So let's break down what was going on here. 50 euro, then 50 plus 30, and 50 plus 30 plus 30. You added on another 30 for the 2 hours. How do we get 140? Well, it's 50 plus 30 plus 30 plus 30. We're breaking it down into how the 140 came about. So that's 50 plus 3 30s. What about if he was there for 7 hours? It'd be 50 plus 7 30s. If he was there for 12 hours, 50 plus 12 30s. And we go a little slower with students, obviously. Now let's introduce a variable. What if he was there for H hours? So we know that the final cost is the call-out charge plus the cost per hour by the number of hours. If he was there for H hours, it would be 50 plus H times 30. So that's the final cost. And we're going to call the final cost Y. Now we have made an equation which generalizes a real-life situation. If he was there for 16 hours, all we'd have to do is substitute 16 for H, and we'd have the total cost. If he charged us 320 euro, could we work backwards and see how many hours he was there for? So 320 is 50 plus 3H. Work backwards, subtract 50 from both sides, divide both sides by 3. He was there for 90 hours. And we see that type of idea. We have the dependent variable, which is the cost. We have the independent variable, which is the time. And we have a relationship here between time and cost. And remember we said we would do algebra through relationships. You could draw a graph of that, but students would need to know how to plot points on a coordinate plane first. And we can see it's a linear relationship. For every hour you go across, you go up 30. And here's another one you could try with students. How much does a taxi cost in Dublin? 380 is the initial charge, like the 50 euro call out, and then so much per kilometre. So what's my cost? It's 380 plus 1.14 by the number of kilometres. Okay, I hope I haven't gone too far over time. So that's it. Is anybody out there still?
Sheelagh, I'm out here, and we've still got everyone who joined. Thanks so much. That was really great, really fantastic. For me, even paced explanations and breakdowns of number and algebra, and there's some great tips in there. I presume for everyone that people would have liked what they saw, little ideas and tips that they can try. So thanks so much, Sheelagh. That was really spot on. I'm going to have a look in. We've come to 12, so we're a little bit tight on time. We mightn't really have time for too much. I'll just read out one or two comments, Sheelagh, if that's okay. Stephanie Cox just saying, not an urgent question, but if you can cover at the end, how are you assessing understanding when delivering remote training? Do you mute learner sessions or encourage an open forum?
I've done a bit of remote training, and what I do is I speak for 5 to 10 minutes. It depends on who I am talking to, how much they can take. And I'm sorry, I was talking there for probably too long, but I stop for about 5 minutes or so, or after 5 minutes, and ask if there are any questions. And I encourage the students then to unmute if somebody has a question and to talk to me. But if they can also write comments, and usually I'm using Zoom. So if there are comments, I can see the comments on Zoom. I know we can't see the comments on this platform, but I can see if a student comes in with a question, because say if I don't stop, you know, I'm going for 7 minutes or so, and a student can't wait until I get to 10 minutes or whatever, they will type in a comment and I will see the question coming up on the screen, and I'll stop then and deal with it.
Okay.
And I also give downtime where, you know, I stop talking altogether for a certain period of time, and I give students time to work on something. And then I will say, hands up, you know, are you ready yet? Now with Zoom, you have sort of a hands up. And if I start, I will start and ask a question then, and I might pick a student's name because I'll have the list of names beside me. How did you get on? How did you get on? Sometimes students will say to me, hold on a second, I'm not finished yet. You know, they just put it in the comments. Wait, just use one word. You won't have to write anything very long. So I don't know if that is helpful, is it? There are breakout rooms as well on Zoom where you can put students into groups and they can communicate with each other. Sorry.
Yeah. Go to, yeah, quite a few of the platforms of breakout rooms, which once you learn how to use them, apparently work well, but I don't know how to use them. But yeah. Okay, Enda Donnelly saying, algebra tiles can also be helpful when looking at the distributive law. Thanks, Enda.
Yes, absolutely, definitely. And also for the idea of what x squared is, you know, the length by the width being exactly the same, you show a square tile, as opposed to maybe 2 by x, which would be a rectangle, which is not a square. Okay.
Okay,
yep,
thanks.
That's great.
David in Cork saying, hi Sheelagh, thank you for that. It's a very hard concept to teach, and you had to reduce numerous lessons into a 1 hour lesson for us. Thank you very much for all the ideas. Well done.
Thank you, David.
Thanks, Sheelagh. You covered a lot in 1 hour. Bridge is saying, excellent, simple, effective, and well presented.
Thank you.
Maria is saying, very good presentation, thanks. Sharona Ferguson saying, thank you, very informative and excellently explained. Michelle Halley saying, great tips for level 3. I also teach level 4, and we have to cover factoring quadratic equations. The main question is when we are going to use this in real life. Do you have an answer I could use for factoring?
For quadratic,
yeah,
quadratic equations?
Yes.
Factoring quadratic equations. Okay, anything that falls under the influence of gravity follows the quadratic graph, you know, the parabola, the upside down shape. So if you describe, say, the path of a golf ball passing through the air, then it will be an ax squared plus bx plus c equation. And when the factors, if you put each factor equal to 0, you know, when you have to solve the equation, you put each factor equal to 0, that represents the position of the golf ball when it's on the ground, when it's on the x-axis. So obviously it's on the ground when you hit it first, so that's the first solution of the quadratic. Goes up into the air, falls back down, so the second time it's on the ground is the second solution of the quadratic equation. I don't know if that's helpful.
Thanks, Sheelagh.
And the other quadratic, the cross section of every single satellite dish on every house in the country is a parabola, which is described by a quadratic function.
Okay, thanks. Michelle, who asked the question, says yes, thanks. So she was happy with your answer, Sheelagh. And the last comment here, we have to wrap it up. Stephanie Cox says, thank you so much. I found today very useful. And Liz McKean saying, thanks very much. Great presentation. Same with Anne Sarsfield. Thanks very much. Well broken down. So it just leaves me to say, thanks again, Sheelagh. We can see from the comments coming in that people really enjoyed it, found it useful, good tips. And as everyone said, you you managed at a lovely, slow, relaxed pace to cram a lot into 50 minutes. So well done on that. So I think there's plenty that people can now take back and use in the classroom or on Zoom or whatever way they're using it. And thanks to everybody who's tuned in. Just to repeat, Sheelagh will send me her presentation and I'll forward it to everybody who has registered, and in a day or 2 or 3 the video recording of this webinar will be on the NALA Ireland YouTube channel. So thanks again, and maybe you'll join us tomorrow, Thursday or Friday, for some of the other numeracy webinars for our Maths Week. So goodbye everyone. I'll close down the webinar. Thanks, Sheelagh.
Thank you very much for everybody for listening in. Thank you.
Bye.
Bye now.